So hello everyone, this is chapter 21 of our reference textbook, University Physics with Modern Physics, Electric Charge and Electric Fields. So far the only force that we have examined is gravity, um, examined closely, is gravity. We've been working with Newton's laws a lot, we've been utilizing kinematics a lot, and now we're concerned with electromagnetism, one of the four fundamental forces which split during the early stages of the universe, and it's one that is inherently way stronger than gravity, but as important as gravity, the basis for chemical bonding, um, biological processes, the this at the heart of many existing technologies today. And so here, as much as I'd like to talk about the concepts or the mechanisms for how things work, we're also going to focus on the application, of course. Firstly, we're going to solve for the number of excess electrons when we're given with a charge. Next, we're going to solve for charge given a charge density or a charge distribution. And lastly, we're going to solve for the Coulomb force felt by a proton in an electric field. We're also going to find its acceleration A and solve for its velocity V prime or Vf at time t. And below I cited in APA our reference textbook by Young and Friedman. So let's start. Excess electrons are placed on a small lead sphere with mass 7.90 grams so that its net charge is negative 3.10 times 10 to the negative 9 coulombs. Find the number of excess electrons on the sphere. Find how many excess electrons there are per lead atom. So we're told to let the atomic mass or the molar mass of lead be 207 grams per mole. So this is a good time to introduce the concept of quantized energy. By the equation Q equals plus minus NE, where Q is the charge of the body in coulombs, N is an integer, and E is a constant equal to positive or negative 1.6 times 10 to the minus 19 coulombs. We should note that E is the smallest magnitude of charge. Any charge that can be isolated or any charge that we can measure is an integer multiple of E. So I highlighted the given here. To start off, to solve for the number of excess electrons on the sphere, we manipulate the equation algebraically. We get to get the number of electrons. So we're talking about an integer here. We divide the charge, total charge of the body, and the magnitude of the charge of one electron, and then it gives out a value for the number of electrons. We then find that 1.94 times 10 to the 10th is the number of excess electrons on the sphere. We divide the mass, we divide the charge of the whole sphere with negative 1.6 times 10 to the negative 19 coulombs. We get this value. To find the number of excess electrons, a number of electrons in excess per lead atom, we divide the mass of the sphere by its molar mass or its atomic mass. That way, grams cancel. After that, we multiply it with Avogadro's number to get the number of the total number of lead atoms in that material or in that sphere. The answer we get from that, 1.94 times 10 to the 10th is the number of excess electrons on the sphere. We get the ratio of that to the total number of atoms. That way, we find the number of electrons in excess per lead atom. So that's what we did there. And we find that 8.43 times 10 to the negative 13th is the number of excess electrons per lead atom. Moving on, signal propagation in neurons. I chose an example in biology just to showcase how physics is really the bedrock of the sciences. It says here that neurons are components of the nervous system of the body that transmit signals as electric impulses travel along their length. These impulses propagate when charge suddenly rushes into and then out of a part of a neuron, or the neuron called an axon. Measurements have shown that during the inflow part of this cycle, approximately 5.6 times 10 to the 11th sodium cations per meter, each with the charge plus E, enter the axon. Now we are asked how many coulombs of charge enter an axon with length 1.3 centimeters during the process. So this is actually a very easy problem. I highlighted a key phrase here, per meter. So the equations that must immediately come to mind are those of charge distribution. Lambda, Q on L, sigma, Q on A, or area, rho, Q on volume. Those are your formulas for linear charge distribution, area charge, and volume charge distribution. Of course, since we have here a unit of length, we deem it appropriate that to use the formula for linear charge distribution. We note that lambda has a unit of charge divided by length. Therefore, if we multiply lambda by length, we are left with a quantity that represents charge. And so we get lambda L equals Q. It's a good practice, although let me just say that it's a good practice to solve for things in variable form first. You do not take things out of variable form until the very end. Now our problems here don't require long solutions, but when it comes to other problems, it's a good practice to solve for things symbolically first without immediately plugging in the values that we already know, even though it's already explicitly stated. We don't just plug them in right away and then solve. We first have to manipulate the equations algebraically first. We do not take things out of variable form. That way, we understand how things work, and most of the time, it gives us more precise values. So going back, we have 5.6 times 10 to the 11th multiplied by 1.6 times 10 to the negative 19 coulombs divided by 1 meter. Because we have here the problem that's per meter. Multiply it by L, 0.013 meters, because we want to maintain SI units. And then that gives us a value for Q. Then we arrive at 1.16 nanocoulombs. That is the amount of charge that enters an axon of length 1.3 centimeters during the process. For our last example, we have a proton. So consider a proton placed in a uniform electric field of 2,950 newtons per coulomb. So we are introduced here to the concept of an electric field. And when we're talking about electric fields, it has the unit newtons per coulomb, or force per charge. Calculate the magnitude of the electric force felt by that proton find the proton's acceleration, find the proton's speed after releasing it into the field. 1.80 microseconds to releasing it in the field, assuming it has an initial velocity of 0. So, one of the equations for the electric field is E equals F over Q. That's why we have the unit newtons per coulomb. If you manipulate the equation algebraically, we get F equals EQ. And since newtons per coulomb times coulomb gives us newtons. So, to find the magnitude of the electric force felt by that proton, we multiply the value for the electric field by the value for the charge of the particle, which is positive 1.6 times 10 to the negative 19 coulombs. We get a value of force equal to 4.72 times 10 to the negative 16 newtons. Now, we are asked to find the proton's acceleration. Now, I have mentioned at the start of the video that we've been using Newton's laws for the physics or the science of the big things. Now we're talking about the small things, but actually in this case, it actually still applies. No? So, we know F is equal to ma. We know that A from there we know that A is equal to F over m. Then 4.72 times 10 to the negative 16 newtons divided by 1.67 times 10 to the minus 27 kilograms, which is the mass of the proton. That gives us a value for the acceleration of the particle. 2.83 times 10 to the 11th meters per second per second. Find the proton's speed after 1.80 microseconds in the field, assuming it starts from rest. We recall the kinematic equation V prime is equal to V naught plus AT. We know that there's no the initial velocity is 0. The equation reduces to Vf equals AT. And then we know the values for that: 2.83 times 10 to the 11th meters per second squared times 1.80 times 10 to the minus 6 seconds. We have your mu there. And we get the value for the final velocity of the proton after 1.8 microseconds into the electric field. It is moving at 5.09 times 10 to the 5th meters per second. There, we've already solved 3 problems together. Now, just to summarize, here are the list of equations that we used. One that is very important in this chapter is actually Coulomb's law. F is equal to K Q1 Q2 or QQ naught, or in some textbooks QQ prime, over the square of the distance between the two charges. So that's also one thing to remember. So thank you very much. I will see you in the next video.